Hi guys, this video covers the binary search tree insertion algorithm. This is the process for inserting a pair into a binary search tree. This is the definition of the operation that we're covering here. Binary search tree insert is given a pair that's meant to be a key value pair. And if the tree does not already contain that pair's key, insert the pair into the tree and return true so that the caller can tell that something happened. Otherwise, meaning that the pair's key was already in the tree, this function does nothing and returns false so that the caller can tell that the insert function call had no effect. So the spirit of insert is that you call it with a pair that is not in the tree, and this insert function puts it into the tree. But if you give it a pair that's already there by mistake, then the function detects that. It doesn't throw an exception or anything. It just returns false. There's a lot going on here, so we're going to factor this into some smaller, more manageable steps. There's this whole if-then logic and finding where to put the node and actually putting the node there. So we're going to break this down into smaller pieces. This is kind of top-down function design where we take a big complicated function and break it into smaller pieces. Here's the pseudocode that we'll create. Insert is given a pair, and we'll say if the tree contains that pair, return false. That's using the contains algorithm or function that we already developed to handle this logic of detecting whether the key is present or not. We don't have to repeat that work. And if that's the case, return false. If we get past the return statement, then we know that the key is not present anywhere, and we'll call a private helper function called InsertNode given the pair. And InsertNode can assume that the key is not present. That will simplify that a little bit. Insert does size plus plus. We have to keep the size int in sync and return true because we know that the insert actually had an effect on the tree. So the insert node function handles just a simplified case. It handles the situation where we're given a pair to insert and we know that the key from the pair is not in the tree already. So insert node knows that it needs to add a new node object to the tree. It's going to change the shape of the tree for sure. That'll make it simpler because we don't have to worry about the case of finding a key already in the way and dealing with that. Also, the insert node function is not responsible for the int size. That's being handled by insert. So when we write insert node, we don't have to think about size. Also, insert handles the return value of true or false, deciding whether to return true to say something did change or false to say nothing changed. So insert node doesn't have to worry about that either. Now let's get into InsertNode. So InsertNode has one job to do, which is to take a pair that needs to go into the tree. We know for sure the pair is not there already, and we need to add a new node to the tree so that the pair is contained in the tree. Here's how we'll do that. First, we find the location where the node would be. If that key were in the tree, we find that location, and that's actually where we'll add a new node. So if the tree is empty to begin with, then the new node that we're about to create becomes the root of the whole tree. That's kind of an easy case. And in that case, the parent of our new node is null. The root does not have a parent. In the non-empty case, things are a little bit more complicated. The new node that we create will be a child of a leaf. So we're going to search for where that node would be if it were contained in the tree. That means we'll reach a leaf at the bottom of the tree and then go past that down a null pointer. And that null pointer that we follow is the location where the new node should go. So the parent of the new node that we create will be that last leaf we see in the searching process. We create a new node object. It will always be a leaf at the bottom of the tree, so its child pointers are both null, and the parent pointer was determined in the step above. Then we have to update the incoming pointer to this child node that we just created. It's one of the tree's root pointer. If this is the first node we're adding to the tree, then the whole tree's root pointer needs to point to this new node. Or if this is not the first node and it has a parent, then either the parent's left child pointer or the parent's right child pointer has to be updated. Those child pointers were pointing at null. Now they need to point at the node we created. So for example, let's say we insert 60 into the binary search tree on the right here. First, what we'll do is the standard search algorithm to locate where 60 would be if it were in the tree, and that would start at 37 and go right and then left and then right. So 60 should be the right child of 55. Then we allocate a new node object. It's a new leaf. So the left and right child pointers of our new node are both null. There's nothing below it. It has the pair that we were given, key 60 is in there. Two things left, the parent pointer and child pointer that form the edge between 55 and 60 need to be filled in. So this was the case of a non-empty tree to begin with. So that search process found the leaf that's the parent of 60, and we update that. And then also the fact that we went off 55's right child pointer at the end means that we have to reassign 55's right child pointer to point to this new node that we just created. Let's see this in pseudocode. So this is my insert node operation. It's given a pair to insert into the tree. Remember, this code assumes and requires that the pair's key is absent from the tree. This assumes that we actually need to create a new node in the tree and change the tree that way. What we're going to do is start at the top and work our way down and keep track of the child node that we're at. This is kind of a bottom node and the parent of that node. This is because when we get down off the bottom of the tree, we'll follow a null pointer. So the lower child pointer will become null at the end. We also need to remember the node that was above that, because otherwise we're left with just a null pointer and we have no way of telling where the search ended. So this is the standard downward search algorithm. We loop until the child lower pointer reaches null down below the bottom of the tree. And every step we just shift down one level. So the parent becomes the old child. The new parent is the old child. That shifts the parent pointer down one level. And then we have to decide how to shift the child pointer down one level. And that's based on the normal comparison. If the pair's key is less than the current child's key, we go left. Child equals child left. Otherwise, child equals child right. Note that we don't need to check for first equaling the child's key because, again, we know that this key is not in the tree anywhere. Then we allocate a new node. The argument order here is first we give it the parent pointer. The parent of this new node is the parent pointer here from the loop. It's a leaf, so the left and right child pointers are null, and then the pair that we're given to insert is stored inside of that node. The only last thing to do is to update the incoming pointer that points at this node. So if the parent is null, that means that we're inserting a root into a currently empty tree. So the root pointer for the whole tree has to become a pointer to this child node that we just created. Otherwise, we know that we just inserted a node below a leaf, and we decide whether to update the left or right pointer accordingly. So if the pair's key is less than the parent's key, then that means the parent's left pointer needs to be reassigned. Otherwise, the parent's right pointer needs to be reassigned. Here's an example. First, let's just see how this actually works in the case of an empty tree. This pseudocode is set up to work correctly in the case of an empty tree. It's a little subtle. So parent and child are initialized to null to begin with. Let's say we're inserting the key 12 into this tree. Over here, the root pointer points at null. It's empty to begin with. So parent is null. Child points at whatever the root is, which is null as well, actually. And then this while loop will not iterate. While child is not null, so child is null. So the while loop doesn't go anywhere, which makes sense because we don't need to seek downward lower into the tree. We allocate a new node with the given pair, and the parent pointer is whatever is in this parent variable, which would be null, which is the right thing to do because this is the new root of the tree. So the child variable updates to point at this new node object. Then we decide which incoming pointer to update, and we're in the first case here. The parent is still null because this is the only node in the tree. So the root pointer for the tree is updated to point at the new node we just created. And that worked. That looks like a correct binary search tree with only one node. Now let's see what happens if we insert one more node after that. So I'm going to insert 7 into this tree with only one node. We initialize parent to null and child to be the root, which points at the first node here, the 12. Then this while loop is going to iterate until child falls off the bottom of the tree, meaning child becomes null. That will only take one step here. So we decide which way to go downward, and we go down the left child pointer of 12 because 7 is less than 12. So parent is pointing at the last node we saw before we went down off the bottom of the tree, and child is pointing at null now to stop the loop. And we reassign child to become a new node object with the parent of the last node that we saw in our downward search and the pair, and it's a leaf, so the left and right child pointers are null. And then we have to update the incoming pointer to that node, and the if else down there correctly decides that the parent's left child pointer needs to point at this child. So then we're done. Finally, let's see how to insert into a larger tree. I've got this example with 4 nodes, and we're going to insert the number 70 in as a key. So the search loop will involve a few iterations here. To begin with, parent points at null and child points at the root of the tree, which is the 37 node. And every iteration of this loop will shift us down 1 level. The parent will go down 1 level and the child will go down 1 level. So to begin with, I'm looking for 70. 70 is greater than 37, so child will move to the right child, pointing at the 61 node. Parent points at the old child node, 37, so you see how they both shifted down a level. This repeats. 70 is greater than 61, so the child pointer is going to go right, and the parent pointer shifts down 1 level. So now child points at 83. We need to do one more iteration. 70 is less than 83, so the child pointer will follow the left child pointer of 83 to a null. So child is pointing at null now, and parent is pointing at 83. The point of this loop is to remember the parent of where the search failed, the second to last pointer that we saw, or the last node, the leaf node, where the search ended. So now we figured that out, and we allocate a new node with parent equaling the parent that we found in that loop. And it's a leaf with left and right child pointers null, and it contains the key that we're trying to insert. Last step is the incoming pointer. So the if statement down there will determine that parent it's not null, so we need to update a node's left or right child pointer. And based on the keys, we need to update the left child pointer to point at the new node. So that's it.